Hi again. We're going to talk about polarization of light now. Now, before we talk about polarization of light, I'm going to talk about an interesting phenomena that was first observed formally in the 1600s, and that is called the birefringence of light in calcite. Calcite is a very common mineral found in Earth's crust, and yes, that is actually the crystal structure of calcite. One of the interesting things about calcite is when you look through it, you'll actually see a double image of what's underneath it. And that property has to do with the polarization of light and how light behaves when it travels through the crystal calcite. Calcite, by the way, is just calcium carbonate. That's the chemical structure. Here's an example. See how there's a double image? So we're going to explain that phenomena today as we talk about the polarization of light. We know that light behaves like a wave, and when we imagine light traveling through space, we have to imagine an electric and magnetic field that are oscillating, that are perpendicular to each other and perpendicular to the direction of travel. The plane on which each transverse wave is oriented isn't always the same though. Let's say we have a light bulb, for example, or the sun. The light waves given off by that luminous source aren't going to have the electric field and magnetic field always aligned on exactly the same plane for every single beam of light. So for example, if we have a source that emits light where the electric and magnetic fields are oriented differently depending on the light ray you're interested in, that light is called unpolarized. So a wave that vibrates in all directions perpendicular to the direction of travel is said to be unpolarized. Here are some examples. I want you to imagine that in this case, the red wave, the red transverse wave represents our electric field and the blue represents our magnetic field. See how the electric field is aligned horizontally here, vertically here, and at some other random angle in these other two light rays. All of this light put together is what we'd eventually see coming from that unpolarized source. Most sources produce unpolarized light. However, if we look at a bunch of light rays where the electric and magnetic field are confined to the same plane for every single light ray, that light is called plane polarized light or linearly polarized light. So let's imagine all of these are light rays coming from some sort of a source or some sort of a surface that was able to polarize all of those beams of light. Whenever we take unpolarized light and we confine the vibrations to just one direction, that's called polarization. You can actually do this with unpolarized light a couple of different ways. One of the best and most efficient ways of doing this is using a filter, something called a polarizer. You can also do this naturally. Light will naturally scatter off clouds in the sky and become somewhat polarized. It'll also bounce off certain surfaces like the surface of water and can become partially or completely polarized. In this image, I want you to imagine we're looking at some unpolarized light. In this example, we're just omitting the magnetic field. So pretend all of these different colors of transverse waves just represent the electric field. Here's our filter. Notice how the filter has little tiny lines that are aligned in only one direction, which allows only one particular polarization to get through. So what gets through? Polarized light. Now these lines actually mean something. In the filter themselves, they can be part of the molecular structure of that particular filter. So how does this relate to calcite? Well, due to the structure of calcite, light is actually broken into two different rays as it travels through calcite. Each of those rays is polarized differently. And each of those rays actually refracts at a different angle as it goes through calcite, meaning two beams emerge. Each of those emerging beams have polarizations that are 90 degrees apart, which is a really unique and interesting feature. That's called polarization by double refraction, or often just called birefringence. A polarizing filter is something that only allows light with a specific polarization to pass through, while light with any other orientation of field gets filtered out. So for example, a Polaroid will do this. So will sunglasses. If you've got some fancy sunglasses that are polarized, they will do this as well. When we use a polarizing filter, light gets polarized in just one plane. If we use a second polarizing filter after the first one, we can actually adjust how much light gets through, depending on the orientation of that second polarizing filter. So in this diagram, we start with some unpolarized light. Our first polarizing filter is called the polarizer. It allows only one orientation of the field to get through. Now, the second polarizing filter is often called the analyzer, depending on how it's oriented. If it's oriented in the same exact direction as the polarizer, all the light will get through. If it's oriented at exactly 90 degrees to the polarizer, no light will get through. If it's somewhere in between, some light will get through, but the intensity will be reduced. In this example, light has become polarized when it's bouncing off the whiteboard. So when a polarizing filter is placed in front of the light, notice how it gets much, much dimmer. That's happening when the polarizing filter orientation is at 90 degrees to the orientation of the polarized light. If unpolarized incident light with some original intensity that we'll call I naught, by the way, the units for intensity are watts, which are units of power, per meter squared, so per unit surface area. If that passes through an ideal polarizer, a perfect polarizer, the intensity of light that gets through will be reduced by half due to the polarization of light. So I1, the intensity passing through the original polarizer, is just equal to half of the original intensity. Once the light is polarized, the second polarizing filter, called the analyzer, comes into play. If it is aligned in exactly the same direction as the original polarizing filter, all of the light will get through. But if it's at 90 degrees, everything is going to get absorbed. Nothing will get through. Let's look at this example here. Let's say this is the orientation of my electric field. In this example, I'm looking head on as the light is heading at me, and I'm just omitting the magnetic field. So we're just looking at the electric field in this example. If my polarizing filter were aligned with the y-axis, the only part of this vector that would be able to pass through my filter would be this EY component. That means the amplitude of my electric field would just be equal to E times cosine of theta. That's all that would get through. The intensity of light is related to the square of the amplitude. So the light that passes through the analyzer will end up having an intensity of I2 equals I1 times cos squared of theta. In this visualization, we can see unpolarized light heading towards a filter that's vertically aligned. For the wave on the left, we can see that as it heads through the filter, the intensity remains the same, because the orientation of this wave, if we just look at the red transverse wave, which would represent our electric field, actually lines up perfectly with our polarizing filter. Here, notice how there's some offset in the orientation of this electromagnetic wave. So the only components that make it through are the ones along the vertical direction. So notice how the amplitude has been decreased as the wave makes its way through the filter. Here, we've got light that's rotated 90 degrees to our original orientation. So none of the light is going to pass through this vertically aligned filter, which means no intensity passes through. Since calcite also splits light into two different polarized rays, it is possible to actually view the two images separately. All you need is a polarizing filter. So in this quick video, you can see what's happening as calcite is placed over some text. Two images are produced. Each one has a different polarization. When a polarizing filter is placed over top and then rotated until it blocks out one of those rays, only one particular polarization of light ends up getting through. Now let's do an example. Again, we've got two polarizing filters at play. The first one is called the polarizer, which is at a certain orientation and will polarize our light. The second one is called the analyzer. So in this example, unpolarized light with an intensity of 20 watts per centimeter squared is incident on two polarizing filters, just like in this image. The axis of the first filter is at an angle of 25 degrees counterclockwise from the vertical. The axis of the second filter is at 62 degrees counterclockwise from the vertical. We need to figure out the intensity of light I2 after it's passed through both filters. The first thing to do in this problem is to make a quick sketch of what's going on. The first filter is aligned 25 degrees to the vertical. The second is at 62 degrees to the vertical, which means the angle between them is 37 degrees. The formula that tells us what intensity of light makes it through the first filter, so I1, it's going from unpolarized light to polarized light. So the intensity that gets through is just half of our original intensity. Going from I1 to I2, now we have to take into account the orientation of our filters. So I2 is equal to I1 times cos squared of theta. Putting these together, I2 is equal to 1/2 times I0. We're just subbing these equations into each other, times cos squared of theta. Plugging in some numbers that were given, and we get a second intensity of 6.38 watts per meter squared. In this demonstration, we have unpolarized light passing through one polarizing filter. This filter is going to act as our polarizer. Now another filter is going to be added. Now that a second polarizing filter is added, when it's aligned with the polarizer, all of the light will pass through. The intensity won't change. When it's at exactly 90 degrees, like right here, compared to the polarizer, barely any light gets through at all. In the second example, we have 3 polarizing filters. The polarizing axis of the second and third filters are at 23 degrees and 62 degrees respectively to that of the first filter. If unpolarized light is incident on our first filter, the light has intensity 7.5 watts per centimeter squared after it passes through all 3 filters. What is the incident intensity of unpolarized light? First, we start with a quick diagram. We're given the orientation of the 3 filters, which means the angle between the first and the second is 23 degrees. The angle between the first and the third is 62 degrees. First off, we know that light as it passes through that first filter is just half of the intensity of the unpolarized light. Passing through the first filter, the intensity is I1 times cos squared of 23, because 23 is the angle between the first and second filter. Plugging these 2 equations in together, we get 1/2 of the original intensity times cos squared of 23. Now we just do the same thing for the other filter. So the intensity passing through the other filter is I2 times cos squared of 39, the angle between the second and the third filter. Plugging all of these things in together, we know this is equal to 7.5 watts per centimeter squared because that's the intensity leaving our stack of filters. Rearranging for I0, plugging in some numbers that were given, and we get an original intensity of 29.3 watts per centimeter squared. Now, as I mentioned before, there are a couple different ways you can polarize light beyond just using a filter. One of the things that can happen is when unpolarized light is reflected off of a surface, it can become polarized along the plane of that surface. So for example, let's say we have a body of water and light is reflecting off that body of water. At an angle of incidence of 0 degrees, the reflected light is still unpolarized. As you increase the angle of incidence, more and more of the reflected light will be polarized. There actually exists one particular angle, a special angle, where all of the reflected light will be polarized. And that special angle is called the Brewster angle. The Brewster angle occurs when the angle of reflection and the angle of refraction are exactly 90 degrees apart. That's the Brewster condition. Let's take a look at where that comes from using Snell's law. Here's Snell's law right here. If we make a quick rearrangement and substitution, since we know the angle of incidence is equal to the angle of reflection, we can come up with this relationship. Now, I just told you, the Brewster angle has a really special property. The reflected ray and the refracted ray are exactly 90 degrees apart, which means the refracted angle is 90 degrees, subtract the reflected angle. Making another substitution into our equation, we can substitute the refracted angle for our reflected angle. Using a trig identity, sine of 90 subtract any angle is just equal to cosine of that angle. Finally rearranging, and we get the Brewster angle is equal to tan inverse of n2, the index of refraction of our second medium, over n1, the index of refraction of our first medium. That's an important equation to keep in mind because we're going to do an example about it right now. So a beam of unpolarized light in air is incident at an angle of 54.5 degrees with respect to the normal on a plain glass surface. The reflected beam is completely linearly polarized. That's telling us that this incident angle is at the Brewster angle. So we can use the equation for the Brewster condition that we just derived. A, what is the refractive index of the glass? Well, we're going to use the condition for the Brewster angle. In air, the index of refraction is pretty much 1. So tan of the Brewster angle, 54.5 degrees, is equal to n2 over 1, which gives us an index of refraction of 1.4. Next question, what is the angle of refraction of the transmitted beam at this initial condition? Well, we can use Snell's law, or we can use the property that I just told you. If you know the reflected angle, you'll know the refracted angle because at the Brewster condition, they're different by exactly 90 degrees. But like I said, we can also use Snell's law. Here's Snell's law. Plugging in the numbers that we just found, we can find that the refracted angle is 35.5 degrees, and that's exactly 90 degrees away from this guy. Finally, there's another interesting way that you can produce polarized light from unpolarized light, and we actually see it in the sky all the time. When light is incident on any material, the electrons in that material will absorb the light, begin to vibrate, and re-emit that light. That effect is called scattering, because when that light is re-emitted by electrons, it's not in the same direction that it originally came from. It's in any direction. The light that is re-radiated by electrons is often polarized. When we view that re-radiated light in the sky, for example, it can appear polarized depending on our vantage point. Here's the cool thing about this effect. It happens at different intensities for different wavelengths of light. So scattering is more strong the smaller the wavelength. If we're talking about visible light, which we are, shorter wavelengths will scatter more strongly than longer wavelengths. Violet and blue light will scatter more strongly than orange and red light. So what that means is if we're standing over here, some nice unpolarized light from the sun, which is made up of all the colors of the visible spectrum, the violet and blue light will scatter more readily in the atmosphere, but the red and orange light will be able to travel the farthest in our atmosphere. So what does this mean? On a nice sunny day when we look up in the sky, we see a blue sky. That's because we're looking at scattered light. At sunrise or sunset, sunlight is passing through more of the atmosphere, which means the blue and the violet and the green light tends to be scattered away. What makes it to our eye? The red and the orange light. That's why sunsets look red and orange. In terms of polarization, if we have an unpolarized source like the sun, the light that's been scattered by 90 degrees compared to the angle it came in on will be completely polarized, whereas light that isn't scattered is completely unpolarized. So the blue light in the sky, when you're looking up at the midday sky, is polarized light. In between, there's some amount of polarization. These are some interesting applications of polarizing of light. Things like polarizing filters are used in photography. 3D glasses at the movie theater are polarized. That's how they work nowadays. Sunglasses can be polarized. They will actually help reduce glare off bodies of water. So if you like fishing or boating, it's probably a good idea to have polarized sunglasses so you can reduce the glare coming off the water. Some solutions have interesting properties where they'll actually polarize light. The liquid crystal display LCD on your calculator is actually polarized. And you can actually investigate the stresses and strains on certain materials by looking at light, polarized light, as it passes through. There's an interesting video that's been posted today that you can watch about this as well.